Okay, now Alan will continue with the lecture about the spin, the proton spin, mass, etc. So whenever you're ready.
Okay. This time I remember to turn the mic on first. Okay, so I went through the mass a bit. I'm going to talk a little bit about the controversy that exists for proton spin. Unlike with the mass, I don't really have a strong opinion, and this is by far going to be the shortest section of these lectures. So the momentum densities are this top row of the energy momentum tensor. For angular momentum, classically, you would define orbital angular momentum as r cross p. Of course, quantum mechanically, that doesn't quite work because you also have intrinsic spin. But if we want to do a angular momentum breakdown, let's see if we can learn something about the orbital angular momentum. So we define an orbital angular momentum density by the cross product of our position with the momentum densities. So we have a Levi-Civita symbol here. Now, there is a note of caution, which is that the wave packet of the proton, since we're defining this for some physical wave packet, can carry orbital angular momentum itself. Is anyone willing to volunteer to catch a Pokeball? Okay. So the idea is if we want to study the angular momentum of, say, some components of the Pokeball, we want its angular momentum relative to some center. However, if the Pokeball itself is moving with respect to some reference point, sorry, I'm a bad catch. That's my fault. Then, well, you're going to get some spurious angular momentum density from the wave packet. This actually ends up being a very important topic in some cutting edge atomic molecular optics applications. There's something called twisted photons in which a photon can carry more than one unit of angular momentum because the wave packet itself twists. Well, the proton wave packet can also twist. So you can get spurious orbital angular momentum from the way that the wave packet is twisting. You can think, for instance, of whenever you have a plane wave, it can be decomposed into a sum over spherical Bessel functions times spherical harmonics. So a plane wave consists of, well, it has indefinite orbital angular momentum. It can carry any unit of orbital angular momentum. So the strategy here will be, I don't think it's necessary, but it's helpful. Consider a proton prepared in a spherical wave packet so you know that the wave packet itself doesn't carry any orbital angular momentum. This is again a case where I probably should have hidden this until the end. So just focus on this part. So kind of like with the mass, what we're going to do is we're going to get the expectation value of this orbital angular momentum operator, defined like so. And we're going to throw in some completeness relations, assuming a proton is a one particle state, sum over all possible momenta and spins. Then we're going to quickly step through doing our variable change into our average momentum and momentum transfer. Next, we're going to have this x from the r cross p, and we're going to rewrite it as a derivative acting on this, and we're going to, well, I skipped through a bunch of stuff. And we're going to quickly do an integration by parts and have it act on everything other than the complex exponential. So we get this minus I here. Now, the only remaining x dependence is this complex exponential, which we turn into a Dirac delta function, which sets the momentum transfer to 0. I'm going to skip the fine details of this, but if you have a spherically symmetric wave packet, it turns out that this component, this part, is stationary around delta equals 0. It only has second order terms in delta, or its derivative at delta equals 0 is 0. So you can apply the product rule. Note that the derivative of this at delta equals 0 is 0. And you are left only with this derivative of this matrix element at delta equals 0. Just like with the mass, you can take the limit of 0 average momentum, although not a plane wave in this case because we are assuming a spherically symmetric wave packet, and you end up with something like this. And if you plug this derivative into the expression for mechanical form factors from so many slides ago, and you assume that you have a state that's spin up along the z-axis, you have to assume a direction for spin in this case, then you'll get that the z component of this operator will be the j form factor minus the s form factor. So the mechanical form factor that corresponds to orbital angular momentum, either a quark or a gluon contribution there too, will be this j minus s. Now, there's a complication that occurs here, a cautionary tale. If you use a different energy momentum tensor, you'll get a different answer for this. If you use the symmetric Bell-Infante, then you have no s at all. So you're only going to get a jg and a jq. And these will sum to 1/2 by G's sum rule, of course. If you use the canonical energy momentum tensor, then you'll get a non-zero s for both the quarks and gluons, though of course with the canonical energy momentum tensor, you have something that's not gauge invariant. And with the kinetic EMT, you have a spin component only for the quark. So there are two primary sum rules that people talk about for spin in the literature. To be sure, there are more sum rules than these two, but these are the most popular. The first, I'm going to point to the Jaffe-Manohar sum rule, which Jaffe-Manohar came up in this paper, very provocatively titled Fact and Fantasy in the Proton Spin Puzzle, or was it the G1 puzzle? Well, it starts with Fact and Fantasy, very provocative title. So the idea here is you start with the canonical energy momentum tensor, which of course has the problem of not being gauge invariant. And you break it up into orbital parts, which you can define using the L cross P operator, and these spin parts, which are end up giving you something that sums to 1/2 in the end. The downside of this is that it's not gauge invariant, but the upside is that they do actually transform like you would expect for rotation generators. I believe I'll get to that on the next slide. The second one is the G-sum rule. Shandong-ji came up with it in this paper. And it's motivated by the kinetic energy tensor, which has an antisymmetric part only for the spin, quark spin. And for the gluons, you just have a total, and you have an orbital quark part, which you can derive from the R cross momentum density, as shown a couple slides ago. It has the perk of being gauge invariant, but the downside of not obeying the algebra you would expect of rotation generators. Okay, so a little bit more depth what I mean about behaving like rotation generators. So the orbital pieces come from the R cross P density, as I said before. Spin pieces come from the Bell-Infante improvement terms. The Bell-Infante will automatically give you what you call orbital as being 1/2. All pieces in this decomposition individually obey the commutation rules for angular momentum generators, which is pretty nice. Moreover, the pieces act like rotation generators for the fields. The quark part of the orbital angular momentum transforms the quark field like you would expect of a rotation generator. And similarly, this is really nice. The problem, of course, was that an echo or was someone else talking? The problem, of course, is that none of this is gauge invariant. And I think the deeper reason for that is that the fields you're transforming here aren't gauge invariant either. If you do a local color gauge transformation, you change what you mean by Q, you change what you mean by the 4 potential, it kind of makes sense that the generators of rotations for these gauge non-invariant fields would also need to not be gauge invariant. There is another practical downside of this particular decomposition that the G decomposition does not suffer, which is the numbers for these are practically unknown, so I don't have a pie chart to tell you. The biggest benefit of the G decomposition, in my opinion, is that we have estimates for the numbers, so we can actually do phenomenology and get a pie chart. So the G decomposition, it's gauge invariant. You don't have these nice algebraic relations. They don't individually obey the spin algebra. They don't generate rotations, but they're gauge invariant and therefore in principle measurable. These actually correspond as well to the zero momentum transfer values of mechanical form factors. They can be estimated from the lattice. And from this particular lattice paper, I got the numbers for this pie chart. So that's kind of what I have to say about spin. I think in practice, most people prefer the G decomposition precisely because you can get numbers for it and make pie charts. That was a very short section, but before I go on to proton pressure, does anyone have any questions or comments they'd like to make? Yeah.
For either of those decomposition, they relate them to. So for either of those two decompositions, can we relate them to the spin or helicity PDF?
The helicity PDF. That's actually a good question, and unfortunately not one that I am completely confident in. Okay, so one thing, the helicity quark PDF can be related to SQ. And SQ is actually the same in both decompositions, as you can see. So that's one thing that we can know. For the SG here, I'm not sure. I think that maybe, might be wrong, not confident in this, that the gluon helicity might be related to this in the light cone gauge. Not 100% sure on that though.
Yeah, because I seem to remember that in CNUGS paper, although there is not a decomposition of gluon angular momentum into the spin and orbital angular momentum, he still related that to this, at least the PDF of gluon in an ad hoc way, saying that, oh, well, the integral of the helicity PDF of the gluon is just the helicity or the spin contribution of the gluon. And the difference between that and the total angular momentum of the gluon is the orbital one.
It does seem a little bit ad hoc.
Yeah, so I don't know whether there is any further developments or criticism.
I'm actually not sure on that. Most of the literature I've seen on the spin, and obviously with how short it is, I'm way less familiar with the spin than the other topics I'm going to talk about. Most people consider the G decomposition to be a 3-term decomposition and the Jaffe-Manohar to be a 4-term. So maybe there's I mean, there are more decompositions than just these two. Maybe there's a variant of G's which breaks down JG further. It will still be different than the Jaffe-Manohar one, to be sure. Something I probably should have mentioned in these slides, but I think I failed to. Yeah, I failed to. The orbital quark part in Jaffe-Manohar and the orbital quark part in G are actually different from each other. So if you were to use the same SG for both, then you would get different orbital gluon parts too.
Thank you.
I have a question regarding the spin of the proton, like how we can understand like spin can provide us like structure and order, right? So how can we understand from these decompositions related to the spin?
Sorry, could you repeat that? I only heard half.
So spin is giving us basic information like order and structure, right? For the proton case.
That's a little bit broad, but I mean, you can have spin in completely structureless point-like targets, But the proton has structure and its spin breaks down depending on that structure. So it is related to structure in some sense.
Okay. And how can we understand these decomposition in terms of angular momentum conservation purpose? Like,
So the way that these are related to angular momentum conservation is that in both of these decompositions, these operators need to sum to 1/2 because the proton has spin 1/2. What exactly each of these terms are individually does depend on the details of the structure. And those are things that you need to suss out either by measuring GPDs or doing a calculation on lattice.
You might have said this and I missed it maybe, but how do you get the numbers of like the quark orbital, quark spin, and gluon like percentages that they make up the total spin?
So the details of this are something you're going to need to ask a lattice person, but my understanding is that they basically just define this operator and they calculate the operator on the lattice. The details of how they calculate the operator on the lattice, I can't tell you. Kostas is giving some lattice lectures, I believe. You could ask him that perhaps. The lattice people doing lattice magic. Well, another way you could get them is if you could measure the mechanical form factors from deeply virtual Compton scattering or related reactions in the G breakdown. And this only works for the G breakdown, not the Jeff and Manohar one. This JG is comes from a Mellon moment of your GPDs. The sum of these comes from a Mellon moment of the GPDs. And the SQ comes from the quark helicity PDF, which is measured in other reactions. So you could also, in principle, get these empirically, but I believe right now SQ is the only one that is well constrained. All right, I guess I'll move on to the proton pressure. I'm way ahead of where I was planning to be. I was planning to start on this one on Wednesday. So chances are I might run out of material before we're done on Wednesday. Oops. All right, so for talking about the proton pressure, we need to talk about the stress tensor. The stress tensor is this 3x3 submatrix of the energy momentum tensor. And the interpretation of it as a stress tensor goes back to what I told you a few slides ago about being able to derive the EMT from local space-time translations. You basically take your field at every point in space-time and perhaps deform it by a different amount. Now, in general, even when your Euler-Lagrange equations are not obeyed, the change that this will make to the action will take this form. You'll get a piece that depends on how you're translating the fields. Symmetrized, this is the linear strain tensor of linear stress theory. You also have an antisymmetric combination, which is the torsion distribution. And the sum of these together, you're literally just decomposing this quantity into a symmetric and antisymmetric part, is contracted with the stress tensor and integrated over all space. In the case that you have a completely closed system that obeys its equations of motion, this will be 0. But if you have some sort of external force that's modifying your system, like you're dealing with the QCD stress tensor, but you are acting on a hadron with some photons, then you can end up doing work by deforming the system. So the deformations you can kind of think of as a virtual pressure gauge, measuring how your system responds to and resists spatial deformations. So at a really fundamental level, the stress tensor has an interpretation as momentum flux densities. Your momentum in a region changes only by momentum flowing into or out of the region through its boundary. There are various ways this can happen. For instance, a particle can go into or out of, you want to catch the Pokeball again, or does someone else want to volunteer? You can have momentum changing because a particle goes into the region or leaves the region. Caught it that time. But you can also have momentum transmitted into a region without particles flowing through it by a particle imparting a force into the region. So you have forces and you have particle fluxes. So there has been a little bit of a kerfuffle and some debate and whatnot about whether the pressure we measure in the proton is really pressure or not. And one of the things that ends up popping up in this debate a lot is whether quarks moving around or particles moving around really constitute pressure or not. And the point I kind of want to make here, and I'm not going to dwell on it too much, is to say kinetic pressure is pressure. If you have a bunch of particles that are moving around randomly, then their momentum flux can be considered pressure. In fact, it's the microscopic origin of gas and fluid pressure. The reason that we feel pressure pushing on us from the atmosphere is because we're being pelted at all sides by air molecules. If you go deep sea diving, or you go into a very poorly made submarine and go very deep into the ocean, it's going to implode because water molecules are pelting it from all sides. Moreover, there are a lot of other cases where particle motion is well understood as constituting pressure. There are services for pressure washing buildings. The Space Needle in Seattle is cleaned by the pressure of a powerful water stream hitting it. Photon flux is the origin of radiation pressure, which is sometimes used to push around solar sails. So I would say kinetic pressure is pressure. And when we talk about proton pressure, we do mean proton pressure, but in general, it's a mix of forces and particle motion. It's not just forces or just particle motion. Now, in one of the intro slides, I showed you a plot from Latifa and Volker's Nature paper with pressures that are both positive and negative. So I want to say something about what positive and negative pressures mean. This is something that you'll find in a lot of engineering texts, although sometimes people kind of switch conventions. For the convention that we use in hadron physics for the energy momentum tensor and the stress tensor, positive pressure means compression, negative pressure means tension. So basically what this means is that if you have a negative stress or negative pressure, the system that's experiencing a negative pressure, I actually had more props besides just the Pokeball, but I didn't anticipate getting to this till Wednesday, so I don't have them with me. But a negative pressure means you're kind of being pulled on from both sides, like one of these poor monkeys. And a positive stress means that you're being pushed on from both sides, like one of these poor turtles. There are a few pieces of literature that claim that the sign of the pressure tells you about whether you have attractive or repulsive forces acting in the local vicinity. But I think that's a little bit misleading. In both the turtles and the monkeys, the primary force responsible for the stress is gravitation. And the turtle on the bottom is under the most stress, the most compression, because, well, the amount of gravitational force acting on him is more because he's carrying more weight. On the other hand, with the monkeys, they're being pulled on, and it's the monkey at the top that's under the most stress because it's carrying the most weight. In both cases, actually, if you take the divergence of the stress, this is something that becomes less positive. So you have a negative divergence, negative gradient. This is something that becomes more negative. So again, a negative gradient. In both cases, the divergence of the stress tensor will give you a negative number, and they'll both give you the gravitational force density. So although pressure tells you about both motion and forces, and the forces might be largely balancing forces such as this, if you want to understand something like a force law or a net force, it's the divergence of the stress tensor you want. Now, all of this so far has been classical analogy. And here's kind of an illustration with the monkeys of how this net force idea works. The net force on this guy, if you account for both the gravitational force acting on him, which you call the body force, and the forces from adjacent cells, the other monkeys, has to add up to 0. So if you add everything except the body force, so just the forces from adjacent cells, the forces from adjacent cells are what the divergence of the stress tensor gives you. And the net force being 0 means that the external force has to be equal to the divergence of the stress tensor. So this is how you can get the external body force acting on a subcomponent of a system by looking at the gradient or the divergence of the stress tensor. So it's a classical idea, but it also works for expectation values in quantum systems. This is actually a really old idea going back to Schrodinger. Other people who wrote about it very early on were Wolfgang Pauli and Richard Feynman. But there was kind of a revolution in the field of applying the quantum stress tensor to condensed matter systems with Nielsen and Martin in the 1980s. Recently, Maxim Polyakov and Son proposed using the same idea to talk about forces on quarks or forces on gluons, so subcomponents of hadrons. Something I found recently is that if you take the stress tensor of the hydrogen atom and apply this same logic, you can actually get out the Coulomb force law. Assuming you didn't know that the Coulomb force law was responsible for electromagnetic attraction in the first place, if you measured the mechanical form factors of the hydrogen atom, you could then learn that from them. So I think it's very exciting to potentially map out the strong nuclear forces by the stress tensor. A bit more complicated since it's a many-body relativistic system. Won't be as easy as the hydrogen atom at all. Now about the divergence-free part. So although the gradient of the stress tensor is what tells you about the force law that's operating, that doesn't mean that it's the only relevant force. So for example, the gravitational force density in either of these donkeys is just going to be rho g. But one of the donkeys is obviously under a lot more distress than the others. And the only thing that differs between them, their C-bar form factors, this divergence of the stress tensor is the same. What we call the D form factor, the part whose divergence vanishes, is different between the two. So this D term, as it's often this D term, as it's often called, tells you about the parts of the stresses that correspond to mutually balancing forces. If you want to be a bit silly, you can remember these donkeys and perhaps call it the donkey term. So the D term isn't just there have been some people who have recently proposed that it's unphysical because it corresponds to a divergence-free part of the stress tensor, but the divergence-free part of the stress tensor for these donkeys is physical and can be felt. All right, so we have this stress tensor and we have an interpretation of it in terms of stresses. Now there's the question of how do you get a spatial distribution out of it? This turns out to be really controversial. And I am going to kick that can down the road and wait until my next lecture to address it. Hopefully I don't go so quickly through this that I have to address it today. But we'll kick that can down the road. For now, we will define a static stress tensor. Now you should keep in mind that this is a definition, not derived, and it's controversial. A lot of people object to it. But the idea is you take the expectation value of your energy momentum tensor operator for plane wave states with equal and opposite momenta, and you Fourier transform over the magnitude and direction of that momentum. This is sometimes called a bright frame distribution, since this matrix element is a matrix element in the bright frame. In terms of mechanical form factors, the stress tensor would contain this D form factor, the donkey term, and this C bar, which tells you about the body force. And the Cauchy momentum equation is the equation that tells you about how the average body force is related to C bar. All right, so in general, you're going to have this complicated 9-component tensor. In the case of the proton, things are more complicated for spin 1, but let's ignore that. For the proton, this is symmetric. This submatrix is symmetric. The anti-symmetric part of the energy momentum tensor only affects angular momentum. So if you have a symmetric 3x3 matrix, then it's always possible to diagonalize it. All of these things are really functions of space. So you have a different diagonalization at each point in space. And this is kind of important. So in your Cartesian frame at a general location in space-time, you can imagine some cube of material inside of the proton with quarks and gluons and whatnot in it. These off-diagonal components of the stress tensor are telling you about forces that are oblique to the surfaces of this material element. And if you have some material element and you act on it with oblique forces, the Pokeball is not a good example. I should have brought some other props. It will shear. And hence these components are called shear stress. However, since a symmetric matrix is always diagonalizable, and diagonalization corresponds to a rotation, you can always rotate the material element so that the stresses are acting normal to the surfaces of the material element, in which case there will no longer be any shear stresses. So when people talk about things like shear in the proton, it's largely an artifact of the fact that your Cartesian frame and the spherical frame are misaligned. So the frame in which your stress tensor is diagonal is called the principal frame or the principal axes, and the components of the stress tensor in this frame are called the principal stresses. And it's a little bit more fundamental to talk about principal stresses than it is to talk about the normal stresses and the shear stresses in an arbitrary frame. So let's make this a little bit more concrete with some pictures and numbers. We'll start with a closed system. We'll assume a proton made of quarks and gluons and summing over all of them so that we don't have to worry about C-bar. Then we just have this Fourier transform with a D form factor in it. A neat trick is that you can use the fact that these deltas here correspond to derivatives acting on this complex exponential, and you can pull the derivatives outside, and you have a Fourier transform just over this D term. I've taken to calling this Fourier transform the Polyakov pressure potential, partly because I like alliteration, but also it was Maxime Polyakov's idea. Now, with this pressure potential, we use a simple tripole model for the D form factor. Tripole meaning you just have a 1 plus delta squared scaled by some unit mass squared factor, and the tripole means you cube it. There's good physical reason to use this. Perturbative QCD tells us that at large momentum transfer, this form factor should go as 1 over delta to the 6th. And we also know that it's going to be some finite number when delta is 0. We call this D0. Now, you can pretend it's a simple homework problem to take this Fourier transform, but you really just get this simple polynomial times an exponential. You can use the easiest way to do it is actually to Fourier transform a dipole squared first and then differentiate with respect to lambda. So if you plug this Polyakov pressure potential in here, you do the derivatives, you end up getting a stress tensor with, well, a few tensor structures. And one of the ways that a lot of people like to organize the tensor structures is into a traceless part and a traceful part. That seems to be a very common thing with tensors. The structure, the quantity multiplying this structure is associated with shear stresses, and the quantity associated with this structure are what people in hadron physics usually call pressure, and I believe a lot of engineers also call pressure, but I think it's a little bit more accurate to call it isotropic pressure because it's an average over pressures in all directions. All right, so let's look at the isotropic pressure, the blue part. Let's get some numbers. There was this Nature paper by Latifi and Volker and FX. They assumed a tripole form for D, and the result they got from a fit to class data is D0 of negative 1.66. One thing, though, is that this only has quarks in it, but is missing C-bar, so it's a little bit incomplete. Now, there was another JLab Nature paper that came out more recently from Whole C data, the JSI-007 experiment, Berger-Duran et al. They got only the gluon part. They didn't get C-bar, they neglected it, but now they have a D0 of G, and they also gave a value for lambda. To be sure, the extraction is model dependent, and they explored this in several different models. The particular approach that I grabbed the numbers from was using the holographic QCD approach for extracting their numbers. And this figure of the gluon pressure comes from a later paper by the same group from the same JSI-007 experiment, but technically a different paper. And then for the total D0, just add both. Use the lambda from the JSI-007 experiment and the expression for the isotropic pressure, which is an average of stresses along all three principal axes, since that's what the trace of a tensor will give you, or 1/3 the trace of a tensor will give you, you get something that looks like this. Looks very similar to both of these figures. So you have something that goes positive, goes negative. I'm going to defer commenting on the interpretation a bit more, except to say that, of course, as I discussed earlier, this corresponds to compressive stress and this to tensile stress, pushing and pulling. The next one is what people usually call the shear stress, the anisotropic or off-diagonal part. It takes this form. It appears to be strictly positive for the proton. It looks kind of like this. Not much else to say yet, except to recall that shear stress is kind of an artifact of misalignment between your Cartesian axes and your principles. So what you want to do is you want to, at each point in space, rotate so that your local frame is aligned with the principal axes, and then talk about the principal stresses. And what you do is you get a radial and a tangential stress. So the radial pressure is basically what you get if you contract your stress tensor with R hat vectors. And for the proton, and in fact for a lot of hadrons, you appear to get something that is strictly positive. The tangential stresses, on the other hand, start out kind of positive, but then go very negative. So this is kind of interesting. Physically, it kind of looks like the proton is, well, kind of like a liquid drop in a certain sense. It has only pressure at short distances, and at long distances, there's a sort of tension tangent to the sphere, orthogonal to the radial direction. But whereas a liquid drop has a very small profile for this tension, the tension is only at the surface, the tension in the proton is extremely diffuse. So you could think of it as sort of like a liquid drop, but with a really diffuse fuzzy boundary. So back to the isotropic pressure. One of the things people really like to talk about with the stress tensor are stability conditions. And there are kind of two that people primarily talk about. One of them is called the von Laue condition, because it was talked about in this early paper by von Laue in the 1910s. Excuse me. This is actually trivially satisfied for every hadron. It can be shown from just, you take the matrix element of your Tij operator between a state with the same momentum, you get 0. It can also be restated as C bar is 0 when you sum over all constituents. But you can see it very nice graphically in the plot of the isotropic pressure, the area above and below the curve on this 4 pi r squared. That should not be PT, that should just be P. That's another typo. Well, the areas are equal, so they'll cancel out. The other stability condition people really like to talk about is the D term being negative at 0 momentum transfer. I'm going to call this Polyakov's conjecture because he was one of the authors on the first paper to postulate it, and he was one of the biggest advocates. But Peter Schweitzer's also been a big advocate of this conjecture. This seems to be true for hadrons, both from the phenomenological extractions by JSI 007 and class, and also from lattice calculations. So for hadrons, it appears to be true. It also seems very intuitive. At short distance, you have compressive pressure that's pushing back against potential collapse. And at long distances, you have tension that's pulling a system against potential disintegration. So it's intuitively appealing. But there is no formal proof that it needs to be satisfied. In fact, there's no formal proof in general relativity of such a condition either. And there are systems for which it is known to be false. The most telling example is the hydrogen atom, which I think is really interesting because the hydrogen atom is like the paradigmatic example of a stable system. So this is something Shandong Ji and his collaborators first showed. The D of the proton is positive. Now, something Shandong and his collaborators did is they assumed an infinitely massive proton, so they were considering the structure just in terms of the electronic orbitals. So they had to, well, the mass of their system was the mass of the electron. It's a perfectly reasonable approach to take for their purposes. But something that I added beyond what Shandong and his collaborators did was I treated the proton as having a finite mass and did the calculation in terms of barycentric and relative coordinates. And if you actually do account for the proton's finite mass and use the hydrogen atom's mass as the mass of your system, not only is D0 positive, it's huge. The mass of the hydrogen atom divided by the reduced mass, so basically the mass of the proton divided by the mass of the electron -1, which is negligible in comparison. D0 of the proton, of the hydrogen atom is huge. And you can see that the Van Law condition is satisfied. Here's your isotropic pressure times R squared, same areas above and below. And multiply by another factor of R squared, and you can see, yeah, the mechanical radius of this is gonna be gigantic. This is going to be very positive. Your D is going to be very positive. So the negativity conjecture for D of 0 appears to be false in general. And there are other counterexamples too. The photon has D0 equal to exactly 1. That is actually protected by gauge invariance. So that will remain the same to any order of any theory that you use to modify the structure of the photon by having some probability of it fluctuating into charged particle-antiparticle pairs. D0 is exactly +1. The electron in QED has a D term that not only is positive, it's infinite, as Andreas Metz, Barbara Pasquini, and Simone Rodini showed. And Andrea Mejia and Peter Schweitzer recently showed, very similar to the electron in QED, if you turn QED on for the proton, so the proton has an electric static field emanating from it, the D term of the proton is positive and infinite too. In the case of electromagnetic systems, there is actually kind of a physical way of understanding this. So this D of 0 is related to, well, the R squared weighted moment of the isotropic pressure. And your electric field from an electrically charged target goes as 1 over R squared at large distances. So the stress tensor, which goes roughly as E squared, goes as 1 over R to the 4th. You multiply by another R squared, you get 1 over R squared. You integrate over all space, you get something that blows up. You have an infrared divergence. So you just have long distance stresses that don't really taper off in the way that you need for this D0 to be a well-defined finite quantity. But not only is it infinite, it's also positive. So this stability condition seems to be false in general. Why it's true for the proton is not very well understood. And since people are still talking about D0 being less than 0 as the stability condition, they're kind of just taking it for granted instead of talking about in detail why. The best hypothesis, in my opinion, I've heard for why D0 is negative for hadrons came from Shandong Ji. He proposed that it's due primarily to a large amount of gluonic radiation. If you have particles moving around, someone want to catch the Pokeball again? Then they actually only give you positive stresses. So if you have a whole bunch of gluonic radiation, that could give you the negative D term you need. Whereas in these atomic systems, you don't really have that many photons buzzing around, pushing on things. You primarily have tensile stress from the pulling of the electrostatic field. Anyway, I do have the section on densities left, but I would like something to save for Wednesday. So I think it's best if I end here and take questions, if that's okay with the organizers.
Are there some questions?
Thanks for the great talk. I'm wondering, like, we have a energy momentum tensor here. Can we define like a spin density tensor?
Yes. There is a definition for it. I don't remember it offhand. I really have to say that spin is kind of my weakest point on all of this. However, Leader in Lorsay is probably the best place to go for anything spin related. I've been kind of advertising it throughout. It does a great job discussing the energy momentum tensor in general, but the primary purpose of this paper is to discuss the spin controversy. They do define a spin tensor though, so you can find it in there.
Okay, thank you.
Thank you for the great lecture. So a naive question I have is, what's the best way to think of the pressure and shear force? Should we picture ourselves as a quark inside the proton, or a small but finite subregion of the proton, as in a classical system?
That's a really good question. So that ultimately gets to something that I did not talk about, although I probably should have, because it is really important for interpretations of the stress tensor, which is what's called the Eulerian picture versus the Lagrangian picture. The Eulerian picture is one in which you primarily think in terms of regions of space that momentum flows into or out of, which is basically the way I have been thinking about it and expressing it in this lecture. So to answer your question, it would be, think about spatial regions. You have forces transmitted into those regions. You have particles moving into or out of those regions. But there is another picture called the Lagrangian picture, in which you think not about regions, but about literal material elements that you follow around while they're moving. So you don't think about spatial regions as the primary structures. For me, it's a little bit more difficult to think about quantum field theory from a Lagrangian point of view as opposed to an Eulerian point of view. The Lagrangian, I mean, this is just my opinion, and probably some other people would disagree with me, but for me, a Lagrangian picture requires having a very concrete material element that you can actually track. And I feel like that requires kind of a classical picture.
Yes, and following that, because the pressure is non-zero, and what is balanced by the color force?
The pressure being non-zero?
Yeah.
So the balance, so the idea of balance here is that what you're calling the pressure corresponds to the magnitude of the balancing parts. So the balancing parts could really be a mix of things. It could be due to the, say, if it's felt by a quark, it can be due to forces exerted by gluons, or it could be due to the quarks entering or exiting a region. So it could be from a mix of things. Using just expectation values, it's kind of hard to tell. And probably, well, we're talking quantum mechanics, it's probably something that's some mix or superposition of these things anyway.
Thank you.
Yeah, could you say a little bit more about what hadrons you've calculated this like a D term for, or D0? And yeah, and if there's anything, I don't know, I guess like special about some of them, or if they're all just like uniquely negative, or just, like, in some huge way. I don't know.
So they've been calculated for a variety of hadrons. Actually, come to think of it, there are some resonances. I can't remember which resonances, but once you have a resonance, you have something that's clearly not a stable system. There have been some resonances for which this D term has been calculated and found to be positive, which is part of the reason that people like Maxime Polyakov and Peter Schweitzer started thinking that maybe it has something to do with stability. If your resonances have positive D and your bound particles have negative D. Of course, the hydrogen counterexample, I think, kind of blows that hypothesis out of the water. But there are resonances for which it's been found to be positive. People have calculated the D term in a variety of baryons and mesons. Actually, since I apparently needed more material, something I probably should have talked about is the D term of the pion is a really interesting one. In the chiral limit, current quark mass is going to 0. The D0 of the pion is exactly -1. This is a rigorous consequence of chiral symmetry breaking, and it holds.
Axial anomaly stuff, or is this?
It's actually not related to the axial anomaly. It's just chiral symmetry breaking. But yeah, it's a rigorous consequence of chiral symmetry breaking. It's been calculated on the lattice. There have been model calculations of it. The NJL model's kind of a nice proxy for studying chiral symmetry breaking. That is a lot more easy to do than QCD. I've calculated the D term of the pion in the NJL model, and it does go to -1 in the chiral limit. So that's pretty neat. Can also calculate it for nuclei. For nuclei, it's consistently negative and becomes more and more negative the heavier nuclei you look at. That's something that's been confirmed by lots of calculations. But electromagnetic systems seem to be a counterexample. They're stable electromagnetic systems for which it's positive.
Okay. Any more questions? Not, let's thank Alan.